today, this is the first time I make a presentation of a new discovery. And I think that this is a major discovery because I have developed a new catalytic system that is capable not only to crack the cellulose and hemicellulose to give a liquid carboxylic acids, but also lignin. And guess what? The products of lignin are more or less the same as carboxylic acids. So this is an amazing system. And when I say carboxylic acid, I mean levulinic acid. Maybe this is not a familiar compound, but this is a very, very interesting compound because it gives you a lot of commercial applications. And you know that the U.S. Department of Energy has selected this among the 12 compounds that they consider as platforms, because from these compounds you can have a lot of applications. So I would like to go. First of all, we have investigated a lot of biomass, and obviously the biomass materials which are of interest to us are residues and waste. For example, forest residues and agriculture waste. And in that case, I have to say that I have successfully tested the straw. Not only the wheat straw, but the rice straw. And why we obviously we don't want to use the normal corn or what we call the amidon, rich materials. So I have to insist on the fact that as a forestry residues, we have a lot. We have a lot in Quebec, British Columbia, in Ontario. And when we talk about wheat straw, we're thinking about the province of Manitoba, Saskatchewan, and Ontario. And obviously, you know that this type of biomass comprises three components: cellulose, hemicellulose, and the binder, which is lignin, very chemically resistant. So every time you want to convert cellulose and hemicellulose, you have to get rid of this lignin. And what people do is an additional pre-treatment phase. And I would like to go through the existing technologies for biomass conversion. And you can see here, let me see the pointer. Yes, it's working. For first generation biofuels, we have ethanol from corn, biodiesel, etc. And bio-oils by pyrolysis. I have to say that in this case, you have a mixture of a lot of compounds that you have to upgrade by hydrogenation. The second generation of biofuels is ethanol from cellulosic biomass, using obviously the lignocellulosic biomass, bioethanol, levulinic acid, sugars, and the new but old process of gasification and fish startup. And the first generation is the AC3B and our BTCA process. I wanted to start with my previous project that I have developed 5 years ago by using a very powerful and let's say selective catalysis system, what I call the oxidative cracking. I can convert the biomass into a lot of chemicals. However, I have in the chemicals the diethylene ether that is quite, recalcitrant to conversion to other products. So I have to use the ZSR5 zeolite. And in that case, I could produce all the hydrocarbons that are produced by petroleum chemistry industry and the petroleum chemistry. However, it was 2014, and we got a crisis. The crisis is you got the price of a crude oil barrel from 110 US dollars to 30. So my AC3B process went, to the death because of its crisis. However, I wanted to show you something, which is very interesting. This is the gene of liquids I have here. And when I use the hydrogen peroxide, I can see, an increase by 30–40% of the gene. And in addition, if I use the Fenton reagent, this is oxidizer with some ions, I can double the yield. And moreover, if I use a polymerization inhibitor to prevent the formation of humins, it's increased up to 80%. This is a product yield not only to levulinic acid, but for 4 carboxylic acids, what I call the main carboxylic acid. Now, we realize that there are 2 phenomena in this reaction. The first one is promoted by ions, the peroxide ion. The second phenomena is the release of energy from the free radicals. So I can say that this is the results of 2 phenomena: oxidation by hydroperoxide, an ion, or even in the case of an acidic medium, a cation. And the energy released by Fenton reaction. You know that this is exactly the same phenomenon that you have by using microwave promote reactions. Because a microwave is called the dielectric radiation that can provide more energy to the reactions. So by controlling the two, coupling the two phenomena, what I can do is here a new process, what is called the BTCA. As a result, I have four main products. Levulinic acid, it's 18 ester, 18 acetate, 18 fumate. And I have to show this slide. The couple here, levulinic esters, levulinic acids, they are called platform chemicals. From these platform chemicals, you can derive a lot of materials or biofuels. For example, here, succinic acid, diphenolic acid, 3-hydroxy propionic acid, methyl tetraethofuran. This is only some examples. Now, why the consumption of this levulinic acid is still very low, 10,000 metric tons per year, because of the production cost. The production cost of levulinic acid is around $3,000 per metric ton. This is the price, the cost given by the Chinese company. And we have an American company that developed what we call the biofine process. During 2 decades, they tried to produce levulinic acid. And they recently announced that they are going to produce levulinic acid at the production cost of little bit more than $1,000 US. I have done with some testing with spews and yellowbirds of Quebec. And as you can see here, I have produced a lot of levulinic acid and 2 18 acetate 18 formates. And these 2 18 acetate 18 format, they have very high conversion value. And mostly 18 format is also a platform chemical. So if I want to skip this before. If I do a preliminary assessment of the economics of my process, the levulinic acid is produced at $600 US. So this is why, because instead of producing one chemical, I'm producing 4. And with 3 of us, they have very large markets, already, a very large market and very, very high value. So I have made a comparison between the American biofine process and ours. And it turns that here, uh, sorry, I'm not very familiar. Anyway, what I can tell you is just 600 US dollars and, now instead of $1,000 as predicted by the Americans. We have done some testing 2 or 3 weeks ago with a lignin jar and using the system. And what we have seen, obviously, we know that lignin can be converted into aromatic, aldehyde or acids like vanillin, etc. If we use a very mild catalytic system, we can stop at the level of the aldehyde or the aromatic acids. But if we go further, we can have carboxylic acids and decarboxylic acid. And guess what kind of decarboxylic acid? We have formic acid, acetic acid, oxalic acid, and succinic acid at a very high level. Our priorities in purchase development. In the next 6 months, we would like to finish the BTCA, at least having the economic and environment assessment. And we would like to deepen our research from the carboxylic acid, levulinic acid, to succinic acid. Because if I can produce levulinic acid at $600, and with such a system, I can predict a production cost of succinic acid around $700 US per metric ton. And obviously, I have opened a new let's say, door from the lignin jar to the carboxylic acids. And when I say lignin jar, I'm thinking about also black liquor. But I know that black liquor is used in North America to produce energy and electricity. I don't know if there is something left for using succinic acid from black liquor. Thank you very much.
I saw that you have made some comparison with the biofine process.
Yeah.
Do you know a bit about this process, levulinic acid?
Yeah, because I have some information from my colleagues. The biofine, they start having a pilot plant in USA, I don't know, New York State, and they try to commercialize. And the first commercial plant was built in Italy, Caserta, Italy, coming from Italy, so I know well these people. And they got a lot of problems because they aim at as main process with levulinic acid. And beside the main products, there is what we call the formic acid, what is quite a valuable product. And they don't know how to recover that. And even now, they are talking about a certain, way to collect this formic acid. In my case, I'm using a mixture of water and ethanol. And formic acid is extremely sensitive to ethanol. And you got 18 format. And you don't have to recover the acid, the formic acid in the acid form. You got the 18 format. And the 18 format has a lot of commercial applications. And also you can, if you want, come back to formic acid with here with a lot of commercial applications.
You have one last question? It's okay? Okay, well, we thank again the government.
I'm sorry for it.